We're going to talk about some real-world network function chaining lessons learned. So briefly, who am I? Ben Goldstone. I work for Dell Technologies. I've been with Dell for a little over 2 years now, working as a senior network engineer, and recently transitioned to manager, managing a number of teams under Dell. So you'll have to excuse me for giving a technical presentation while being a manager, but here we are. So we're going to talk today about what is network function virtualization, why might you want to use it, some requirements for building such a solution. And these requirements and these lessons learned specifically come out of a use case that we built for a customer over about the past 2 years. So this is a system that is used in production. A lot of traffic runs through it. I have abbreviated things and tightened it up specifically so there isn't any customer-specific data here, and I will be slightly restricted on what questions I can answer and to the depth that I can answer them. But hopefully this will give you a good overview of how to build such a solution and some of the issues and pitfalls that you can avoid running into. Then we'll talk about network function chaining or service chaining and how we accomplish that through a network fabric. And of course, how can we evolve this for future use cases? So I'm sure most of you here were attracted to this talk because you know what NFV is, but in short, NFV is taking virtualized versions of traditional hardware appliances and running them on standard compute. We interconnect that via network connectivity fabric, and ultimately that gives us some positive capabilities like you don't have some of the traditional forklift upgrades like you'd have with hardware. Instead, you can increase memory, CPU, et cetera, to aid in adding additional capacity. However, virtualized appliances are not always the correct solution. There are circumstances where you need ASIC support for large table sizes, for instance, or ACL processing, things like that. But for certain use cases, the virtualized versions do a very good job and meet your use case. Ultimately, we also get some really nice ability to link these network functions together, which is part of what we'll be talking about. So instead of having to physically plug and unplug cables like you would with hardware appliances to link them together in different ways, you have the ability to more elegantly interconnect your different network functions within the network fabric and within the different compute instances. That's where we come to composable and recomposition, which when we're saying composable, we're not necessarily talking about composable infrastructure as perhaps you've heard in the past. Instead, we're saying you can create compositions of network functions and tie them together in different ways to solve different problems. And similarly, if you need to recompose the network functions that you have within a certain circumstance, you can insert or remove them as needed. Now, I want to specify that there are existing standards, like the NFV standard that describes how to build a good portion of this system. Not necessarily replacing that standard. What we're doing is talking about how you can implement specifically the network fabric to support network function virtualization, and some lessons learned around how to do that on the compute side and on the network side. So let's start with the compute side itself. In terms of shuttling traffic in and out of these different network functions, the functions themselves run on compute instances, generally on top of a hypervisor. In this case, we are talking about virtual machine-based network functions or network appliances instead of containerized virtual appliances, but some of the concepts here can apply to either. In this instance, we did use SR-IOV in particular to be able to create virtual functions within the SR-IOV context, which create separate I/O queues for shuttling traffic in and out of virtual NICs that exist then within the hypervisor. Those NICs can then be subdivided into sub-interfaces. Those sub-interfaces are then connected to different virtual network functions. This is very important because this design here informs how we're going to build out the network itself at scale and use specifically double tagging, double VLAN tagging, for being able to shuttle traffic in and out of these hypervisors and in and out of these virtual machines effectively. Any questions about this part of it? And of course, if you have questions as we go along, just raise your hand. I will mention that SR-IOV also provides us some near hardware level performance. It's not quite just bare metal performance, but it's very close to it. So you don't have a lot of overhead like you do with other applications there. So we take those hypervisors with NICs capable of SR-IOV and the virtual functions that we build out in the SR-IOV context. We connect them to a VXLAN fabric. We're specifically going to use VXLAN here instead of some other technologies, as it's standards-based, fairly ubiquitous, does exist within the SONiC ecosystem, which is what this is built on top of, specifically Dell Enterprise SONiC, but we are working to bring some of these features that we'll get into here in a minute into the community version of SONiC as well. So we could have a whole talk on why VXLAN EVPN instead of traditional layer 2 networks, but suffice to say that we gain a lot of capabilities having a routed topology rather than a traditional spanning tree-based topology. So that's why we're building the core of the network based on VXLAN EVPN. It also scales very significantly as you have a 24-bit address space or namespace to use rather than the traditional 12-bit namespace that you'd have with single VLAN tags. Now here's where we start to get a little creative. We're going to use double tagging and VLAN translation combined with some of those SR-IOV virtual function contexts that we mentioned previously to scalably send traffic across the network and into these hypervisors and into these virtual functions. We are specifically using what we call double tagging. The presentation says Q-in-Q because that is the traditional application for double tagging, but we're actually not doing true Q-in-Q in this use case. We're simply creatively using the concept of having 2 or potentially more VLAN tags to shuttle information in and out of these hypervisors in an effective way. The other thing to note is because of that, traditionally the TPID of that S tag is specified to be the TPID of 88A8. That is traditionally the specification. However, here we're actually going to be pushing that external tag on with the traditional TPID of 8100. So you'll actually have 2 8100 specified tags on this frame. That's fine for our application. You'll see why in a second. So, as I said, this is where we're getting creative. The key component here is that we're actually using that outer tag to designate the destination virtual network function, the network function itself. And then we're using the inner tag to correctly select the interface on that virtual network function. If you picture this at scale, you might be running dozens or hundreds of these virtual network functions on a single compute instance, and you need a way to delineate the virtual network function it's destined for first, followed by the specific virtual network interface on that virtual network function that traffic is destined to. So that's why we're using that combination of S tag and C tag in this creative way. So as the traffic enters into leaf 3 across that VXLAN EVPN network and then traverses from leaf 3 into the compute instance, you'll see that S tag is removed specifically by that SR-IOV virtual function. That SR-IOV virtual function says, because of this designated S tag that it had on this frame that I now have removed, that is destined for this IOQ. That IOQ then progresses to the correct virtual network function on which we have an interface. So here is part of the key here. Working from left to right, you'll see what we're really building out is an entire path, and this becomes important for the controller. So we start with a single tagged frame on the left side, egressing that virtual network function. A tag is then added by that SR-IOV virtual function so that the tag progressing across that red line from Ethernet 1 to leaf 3 has 2 tags. And we have to get creative again because today within SONiC, we don't have the ability to actually track a tag set within the system. We can only do pushing and pulling of tags, but ultimately in the MAC address learning table, every entry is mapped to a single VLAN tag. That's an improvement that we'll talk about a little bit later. So That pair of tags, per the rule within the switch, is mapped to VLAN 300, a single VLAN tag. And in this case, that's really a named bridge. So we're creatively using that named bridging concept. That is then sent into the VXLAN overlay between leaf 3 and leaf 6, traditionally over spine, not depicted here. And that traffic is VLAN encapsulated when it's routed between those leaves. As it egresses leaf 6, the VNI to VLAN mapping occurs in reverse. It is on egress from leaf 6, typically going to wind up being double tagged. So we do a VNI to VLAN mapping and then push a tag on. Send it down to Ethernet 2 on comp unit 2. It then, in reverse, will use that SR-IOV virtual function to strip that outer tag and send it on to its destination. A little tedious, but it's important for how this system works, and this is part of what it took us a little while to actually work out all the kinks of, and what initiated Dell Technologies to actually add both double tagging and VLAN translation to Dell Enterprise Sonic. The two features we are working to ultimately bring to Community Sonic so that it also supports this kind of use case. Another way of looking at it, we don't need to go through this whole thing again, but when you're actually building a controller, which is part of the prescription here, for how to automate the underlying network infrastructure, what you need to do is realize that ultimately you're building a path. That path is from one virtual network function to the other, left to right. Bear in mind those virtual network functions may be on the same host, they may be on different hosts. That ultimately translates into a set of segment IDs. That's each of the colored lines, black, red, green, blue, black. Your controller needs to know how to program that entire path ID divided up by those segment IDs. And as you can see, if you look at the encapsulation method, we're going to hop from 802.1q, single tagging, to AD, double tagging, VXLAN EVPN, then back to AD, then back to 802.1q, single tags. You'll also notice that as we're transitioning across that network, while each of the switches alone has a MAC address table limitation where each of the switches can track about 4,000 VLAN IDs, so there is that limitation per individual switch, because we're actually able to translate from an arbitrary VXLAN VNI like 62,300 to any set of any specific VLAN ID. In this case, we're using this named bridge within the system. We actually can utilize that full 24-bit namespace. So we can support up to about 16 million entities here. In practice, I can't give you the exact number of scale in terms of scalability that this customer has running in production, but as of today, it's in the low thousands approximately. And this can scale up to tens or even hundreds of thousands in terms of the network fabric. Your limitation within this environment is going to be on the compute side. How many instances can you host on the compute side? And as we found, ultimately, how many SR-IOV virtual functions will your NIC support? That tends to be the ultimate limitation. Do note that this fabric was also built to support non-virtualized devices. This customer does have some hardware appliances that they also run in their infrastructure. And so ingress, egress from those devices with just a single tag is also supported. You can have a double tag on the virtualized side, single tag on the other, mix and match as you like. This environment will support both. I won't run through these code examples in exceptional depth, just for the sake of time. I added them here, so if you would like to take a screenshot of them or you'd like a copy of the presentation, you can have that reference. But this is what it actually looks like if you're within the Sonic CLI and you need to implement, in this case, double tagging. And of course, there's a commensurate API call. Some practical examples for the same. VLAN translation also has a simple example and a simple command set that you can run through. So if you need to convert one VLAN ID, either the outer or the inner tag, if you need to change that from one number to the other, it's very simple to program that. And of course, some practical examples there. Now, I promised you we'd talk a little bit about service chaining. So this is a somewhat overly simple example, admittedly, but I want to start here just for the sake of illustrating the concept. So whether you have remote users, external customers, or remote office users, maybe a whole cadre of them, they need to access ultimately resources on the left side, file servers, web applications, say Active Directory servers, databases, whatever it may be. And so what we're building out in this infrastructure and what this customer does have running in production are things like NAT or CG-NAT functions, firewall and VPNs, web application firewalls, load balancers, and so forth. They also, in the specific environment I'm referencing, have the ability for customers to be able to bring their own network functions. Another nice thing to be able to enable. Customers can, because there's a user interface as well as an administrative interface, they can then create arbitrary sets of changed network functions, and these network functions can exist on a single host or multiple hosts across this fabric. Ultimately, the network traffic will ingress the fabric on a border, typically a border leaf, from the external internet or from a remote source, transit through the network functions, through NAT, firewall, and so forth, and then ultimately egress that environment either further into the data center or externally into the customer's environment. Some considerations that I want you to bear in mind for service chaining that do potentially cause some issues if you aren't using the right chipset, the right NIC, and or the network operating system that you're utilizing doesn't enable some of this functionality. You can have network functions that are on the same host. They're separate network functions, but the traffic is going to ingress and egress on separate physical ports. You can also have the use case, and one of the more complicated ones is when traffic needs to go from one single host, from one network function, out a physical port, up to the switch, return on that same physical port, so immediately hairpin, come back in on that same port, and then ingress into a different virtual network function. Because again, we can map those SR-IOV virtual functions independently to different virtual network functions via those different I/O queues. So you do need the ability for your switch and your switch operating system to support that kind of hairpinning through the switch. Now, we specifically wanted to be able to support that, as through testing we found that while some of the NICs that this customer was using did have the ability to leverage, in this case they were Intel NICs, leverage a layer 2 switch built into the NIC itself, there were some throughput limitations that were found with that. And ultimately, we moved away from that model and instead decided to actually send that out to the switch to be able to do that at line rate without any of those limitations. So something you might want to bear in mind if you build something like this yourself. Of course, we also have the example of just sending between different hosts, which is what we illustrated before. And this system is also built to be able to send directly to things like cloud service providers. If you've ever had an NNI configured with, like, for instance, Microsoft Azure, a directly connected NNI, not a brokered one, you'll find that you do wind up needing double tags when you're sending that traffic into Azure. So part of the goal here was for the network fabric itself to be able to directly support connections to cloud service providers that do require a double tagged NNI without having to go through an additional router. These same features support that. In terms of scalability, within a single network fabric, you can support up to thousands or tens of thousands of entities. And then, of course, for either high availability or because you have these network functions separated by geography, or simply for additional scalability, you can use the data center interconnect functionality that we introduced to Dell Enterprise Sonic recently. There's another feature that's being hopefully brought into Community Sonic at some point, to be able to scalably interconnect additional separate EVPN VXLAN fabrics across that DCI link, which will give you that same layer 2 adjacency. And then when you ingress further into that fabric, you can use that same double tagging feature to be able to send traffic to those VNFs with both tags. All right. One last thing I wanted to include, this is not the actual architecture that the customer used. This is actually an architecture I built for a different customer a while back, but is just as applicable here. I wanted to just highlight this because this does support the same type of use case we've been talking about. If you want to build this for yourself, taking this type of reference architecture along with the reference network architecture we just talked about, utilizing EVPN and the double tagging feature, will get you very far to be able to building your own VNF or NFV clusters for use for your own customers. Now, what we've been talking about thus far is mostly constrained to that bottom right-hand part of this picture, the data center, and where you have devices under management, different switches that form that fabric. Oftentimes, what you'll want is an agent set that is separate from the fabric that allows you to scalably send command and control, not in the malicious context, but command and control in terms of network configuration down to those switches. And oftentimes, the control system will be hosted centrally while the actual network function virtualization clusters will be distributed out across different data centers. So having that agent set, that local agent that can receive that control information of how to program that fabric from a centralized location and then push that down into the switches gives you a very scalable model. The rest of this is just for reference. You don't have to build it like this, but it gives you an idea of how you might build out such a system. In summary, part of what we've learned is that you need to track the end-to-end flows in the terms of segments that ultimately give you an end-to-end path. So I don't have a project that I can introduce you today. I wish I did. That actually solved the software side of this equation. That gives you a controller that you can use to build this. There are some open source solutions that you might look into. Oftentimes, this type of controller, and in this specific environment, I can share that this was the compute side was hosted on OpenStack, which is very common for service providers. But the controller was something they built in-house as a proprietary feature, along with their web interface. So if you're looking to do this, I would strongly urge you to consider building some sort of controller and have that controller start to solve the problem of tracking those end-to-end flows via segments. Now, double tagging is useful, and we made creative use of it here, but there might be better ways to do this. Admittedly, this is not the only way to do this by any means. We'll talk about some of those in just a second. We did find that SR-IOV is very usable in this context. It scales pretty well. It's pretty well supported across a variety of different NICs that you can get from different vendors. And we didn't run into that many issues. There were a couple of things where we needed to update some firmware. One specific case where we did need to notify Intel of a problem on their specific NICs that were being used, but overall, it's a relatively mature technology. SR-IOV has been around for quite a while. As I said, you do need to ultimately build an orchestration layer and administrative/customer GUI to be able to actually administer this and enable your customers to use this at scale. Some additional things that we're considering are things like being able to add what's traditionally called service provider style bridging, not actual service provider bridging, but service provider style bridging, where you can have named bridges that are not just VLAN 200, VLAN 300. Instead, you could actually name a bridge, create a named bridge, and then dynamically insert interfaces into that bridge, which would give you a lot more scalability and really simplify the configuration. So something we're talking about adding internally to Dell Enterprise Sonic. If we do that, we'll talk about bringing it down into Community Sonic. I will say that one is a much longer conversation because it requires a lot of work at the SI layer and the internal architecture of Sonic itself. We do actually today have traffic policing capabilities, and that is used by this customer to great effect to ensure that customers aren't outstripping or outrunning their allocated bandwidth. So bear in mind, as you build this type of system, you do want to have that implemented, preferably in the network fabric, so that you can support both hardware appliances and virtualized compute nodes, hypervisors. There are also ways to implement that in the hypervisor itself. Some alternatives, as I promised, for how you might improve this over double tagging, the way we've used it here, are things like utilizing segment routing or something similar to that instead of VXLAN EVPN plus double tagging to be able to more effectively build out a scalable network and preferably you'd be able to actually do some of that segment routing label stack implementation within the hypervisor itself and have that hardware offloaded on the NIC. Alternatively, you could also look at moving the VTEP, that virtual tunnel endpoint, into the NIC itself. ConnectX NICs, for instance, will support this. And I've done something very similar to this at a previous job where we used ConnectX-5 NICs plus a library called TC-Flower to be able to do hardware offloaded VXLAN to VLAN translation in a very scalable, dynamic way. So that's also an alternative. We did talk to the customer about it in this use case, but the hardware they already had and the hardware they had selected didn't specifically support this. So we went with this other creative approach instead. Also make sure that your switch NPU in particular does support the features required. You'll, in the Broadcom family, which is the one I'm more familiar with, typically find this in the Trident series of ASICs. Some of the Tomahawk ASICs don't necessarily support some of the features that we've discussed. So do make sure that your switch supports these things. Another consideration that we've discussed, and I've used again at a previous place of employment, was DPDK-based system, which would be another alternative here. It does introduce some complexity because you are actually taking those virtual NICs offline, out of visibility of the kernel, and you need to use ring buffers and so forth to be able to process that traffic. And it requires typically some custom written code to be able to do that packet processing. But you could potentially build out a platform based on DPDK as an alternative to the SR-IOV implementation. That brings us to the end. If there are any questions, we got about 3.5 minutes to answer any, or you guys can go get some drinks. All right. Thank you, guys.